Hello everyone, welcome to Pyman Tutoring. Today we are looking at some example questions from the electromagnetism unit, starting with parallel plate and point charge problems. So this is the problem we're dealing with. It's parallel plates arranged as shown in the diagram. There are 4 parallel plates, 2 vertical, A and B, and 2 horizontal, C and D. We've got an electron that's starting from position A and is making its way through the horizontal electric field, through this hole in plate B, where it's then going to come under the influence of the electric field between plates C and D, and we're going to see that it's going to be deflected upwards by that field, and at some point it's going to strike plate C. We're asked 5 questions. In the first part, we want to know the speed of the electron once it hits plate B. We want to know the force acting on the electron when it's between plate C and D, the time it takes to actually strike the plate, and then also the distance that it travels before it strikes plate C. So those are the 4 things we're being asked to do. So let's see how we tackle this. So the first question is to determine the velocity of the electron once it reaches plate A. So the electron is going to travel across this electric field and arrive at plate B with some velocity. How do we calculate that? Using the fact that voltage or potential is just the potential energy per unit charge. Let's just quickly look at that with a little graph. Here is plate A, here is plate B. We know that at plate A we are sitting at 60 volts, and at plate B we are at 160 volts. And so this is voltage or potential. And so the potential is starting at 60 volts and is climbing linearly up to 160 volts once we reach plate B. Now, if you remember the units of potential or volts, a volt is the same as a joule per coulomb. Or J over C. 1 volt is 1 joule per coulomb. And that means that if we move 1 coulomb of charge through 1 volt of potential difference, we exchange 1 joule of energy with the field. So we can simply write that the change in energy is equal to the change in voltage, or the change in potential, multiplied by the amount of charge that we're moving. Remember, if the charge is 1, then the change in energy will just be the same as the change in voltage, but converted into joules. Here we have an electron that we are moving from plate A to plate B, and so the change in energy of that electron as we move from plate A to plate B is the voltage difference between A and B, which we know is 100 volts, and the charge on the electron, 1.6 times 10 to the minus 19 joules. Now this electron is moving from a positive 60 volt potential to a positive 160 volt potential. So it's going to be attracted to plate B and therefore is going to be accelerated and will gain kinetic energy. And basically we can say that the energy gained by the electron is equal to its increase in kinetic energy. And we know that kinetic energy can be written as 1/2 mv squared. And so this enables us to determine the value of v, the velocity, when we reach plate B. We simply calculate the energy change, and then we will divide by 1/2 m and take the square root. So v is going to be equal to 2 times the change in energy divided by the mass of the electron, and then we're going to take the square root of both sides. And that is equal to square root of 2 times 1.6 times 10 to the minus 17, because we multiplied the charge by 100 to get the energy, divided by the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms. Plug that into your calculator and you will obtain a velocity of 5.93 times 10 to the 6 meters per second. That is the velocity of the electron once it reaches plate B. Part B of the question is to find the electric force acting on the electron between plates C and D. So to find this, we first of all look at the voltage difference between C and D, and we see that it's 200 volts. The distance between C and D is 8 centimeters. That's 8 times 10 to the minus 2 meters. Always convert everything into meters. And so we're now able to calculate the electric field. E is equal to the voltage divided by the distance. So that's 200 divided by 8 times 10 to the minus 2. And that gives us an electric field of 2,500 volts per meter. That's the electric field strength. And to find the force acting on the electron, we use the equation force is equal to the electric field multiplied by the charge that it's acting on. In this case, the charge on an electron. And therefore, we can say that it's 2,500 volts per meter multiplied by 1.6 times 10 to the minus 19 coulombs, the charge on the electron, and the units there would be newtons. And because the plate C is positive, the electron is going to be pulled vertically, so we can also show the direction of this force in square brackets as up, and that works out to be 4 times 10 to the minus 16 newtons in the up direction. Okay, on to part C. Now part C asks us for the acceleration that the electron experiences between plates C and D. Now we've just calculated the upward force, the electrostatic force pulling the electron upwards. Strictly speaking, there's also the gravitational force pulling the electron down, but of course it's very small. But if we do the free body diagram, we've got electric force acting upwards, and we have the gravitational force acting downwards. And we can say that the net force which is obviously in the upward direction, will be the electric force minus the gravitational force. And we just calculated the electric force. We said it was 4 times 10 to the minus 16 newtons. And the gravitational force will just be the mass times the acceleration due to gravity. So that will be 9.11 times 10 to the minus 31 for the mass of the electron, multiplied by 9.81 meters per second squared for the acceleration due to gravity. And of course, since the order of magnitude for this gravitational field portion of the equation is so many orders of magnitude smaller than the electric force, the answer is basically the electric force. Newtons. And from this we can get the acceleration. Acceleration is equal to the force divided by the mass, Newton's second law, and that gives us 4 times 10 to the minus 16 newtons divided by the mass of the electron, which again is 9.11 times 10 to the minus 31 kilograms, giving us an overall acceleration of 4.39 times 10 to the 14 meters per second squared. That is the acceleration vertically in the electric field created by C and D. Now we can move on to part D of the question. So part D asks us to find the time it takes for the electron to strike plate C. So we know, just going back up to the diagram, that the electron is going to come through the gap in plate B. It's going to be coming under the influence of this electrostatic field, and then is going to strike the plate sometime after coming through that hole. To do this, we look at the motion in the vertical direction only. We can say that the acceleration vertically is, as we just calculated, 4.39 times 10 to the 14 meters per second squared. The initial velocity vertically is 0. It doesn't have any vertical velocity, and therefore we can use our kinematic equation. Distance is initial velocity plus 1/2 a t squared. And this allows us to solve, because the distance we're looking to travel vertically is 4 centimeters, so that's our S. Put that in terms of meters, is 0.04, is equal to the initial velocity vertically, which is 0, times time. So clearly that's nothing, plus 1/2 multiplied by 4.39 times 10 to the 14 for the A, multiplied by t squared, where t is the time that we're looking for. Now we can rearrange that equation to find that t is equal to 2 times 0.04. That's just taking this 1/2 term to the other side of the equation, dividing by the acceleration, 4.39 times 10 to the 14, takes this term to the other side of the equation, and then we're left with t squared. So to get t, we simply have to take the square root of that expression. And if you do that, you will find that delta t, or the time taken to strike the plate, is 1.35 times 10 to the minus 8 seconds. Okay, so at that point we can move on to the very last part of the question, part E. The part E wants us to find the distance that the electron travels after passing through plate B and before striking plate C. So we can find that distance by taking the horizontal velocity, which we calculated to be 5.93 times 10 to the 6, and multiplying by the time that we calculated in part D, which was 1.35 times 10 to the minus 8 seconds. And that gives us a distance of 0.08 meters, which is just 8 centimeters. So in this part of the problem, we're assuming that the horizontal velocity is constant at 5.93 times 10 to the 6 meters per second, and therefore the distance traveled in the horizontal direction is simply the horizontal component of velocity multiplied by the time for which the electron is following that trajectory. What we're ignoring here is any effect that plate B has on slowing down the electron by pulling back on it once it passes through the hole in plate B. Okay, and that concludes this question. I hope you found this explanation useful. If you did, please hit the subscribe button and click on the like button. And if you tap on the bell when you subscribe, you'll also receive updates whenever a new video is posted. Thank you very much.